Today we discuss an example of a metric space, that the space of all bounded sequences is a metric space. We have a set X which consists of all the sequences which are bounded, means uh, for all n, mod of each term is less than or equal to some non-negative number. Then the map d from x cross x to r defined by d of xy, where xy belongs to the set X. D of xy is equal to supremum of mod of xi minus yi, where supremum is taken over I, um, is a metric on x. So here D is defined by this expression, that D of xy is equal to supremum over I mod of xi minus yi, where I is from 1 to infinity. So we prove the first property, that D of xy is non-negative. Here, since we know that for all uh, I means the supremum of this set x mod of x1 minus y1 mod of x2 minus y2 and so on. What is the supremum of this set? Since each modulus is non-negative definitely, and so their supremum, which is the least upper bound, this will be also non-negative. Okay, so it is not difficult to verify that the supremum of this set is non-negative. So hence d of xy is non-negative. So you guys must know the definition of least upper bound and greatest lower bound. All these definitions, they are very simple. The second property is, we prove that d of xy is equal to 0 if and only if x is equal to y. So here d of xy, if it is equal to 0, then this implies that supremum over I mod of xi minus yi, that's equal to 0. So since the supremum of um, this set is equal to 0, if I write once again that x1 minus y1 mod and x2 minus y2 mod and so on, if the supremum of this set is equal to 0, so and supremum is the least upper bound, means uh, the supremum of this set uh, is a number which is greater than or equal to each element of this set, means this is definitely supremum is also an upper bound, and this is the least upper bound. So if the supremum is equal to 0, so it means that each modulus is equal to 0. Hence for all I, each modulus of xi minus yi is equal to 0. So by the definition of modulus, if the mod of x is equal to 0, it means x is equal to 0. Hence xi minus yi is equal to 0 for all I, and this implies that for all I, xi is equal to yi, where xi and yi, they are the real numbers, so the sequences x and y, they are equal. Okay, so we go in the reverse direction to prove the converse. this is simple. So hence d of xy is equal to 0 if and only if x is equal to y. Next, d of xy is equal to supremum over I mod of xi minus yi, that's equal to supremum of yi minus xi. This is equal to d of x. Sorry, that's equal to d of yx. Hence d of xy is equal to d of yx. Here we use the property that mod of a minus b is equal to mod of b minus a. Next, the triangle inequality. We verify the triangle inequality. So we take the third element z, which belongs to x. Let's suppose that z belongs to x. So it means that then you can say z is a sequence which is bounded. So z has the form z I from 1 to infinity. So we shall prove the triangle inequality here. So for all I, we can write xi minus zi in this way, xi minus yi plus yi minus zi. We add and subtract yi, and then by the definition of uh, by the property of modulus of real numbers, we know that mod of a minus b, that's less than or equal to mod of a plus mod of b. So we use sorry here mod of a plus b, which is less than or equal to mod of a plus mod of b. So we use this inequality. Then we get mod of xi minus yi plus mod of yi minus zi, and definitely this is less than or equal to its this element. Supremum of mod of xi minus y, and also this will be less than or equal to supremum of yi minus zi, and hence this implies that for all I, mod of xi minus zi, that is less than or equal to, this is equal to d of xy, and that's equal to d of y z. So here we shall write d of xy plus d of yz. So this is the upper bound of this set means for all I this is less than or equal to this number. It means that uh, this expression is an upper bound of this set mod of x1 minus z1 mod of x2 minus z2 and so on. So when we take the supremum of this set, if we have the supremum of this set, if it is equal to t, so definitely the as we know that the supremum is the least upper bound, so this will be less than or equal to any other upper bound. So this t will be less than or equal to uh, d of xy plus d of yz. So it means that the supremum of this set mod of x1 minus z1 mod of x2 minus z2, it will be and so on, it will be less than or equal to d of xy plus d of yz, because this is the least upper bound. This value is the least upper bound of the set mod of x1 minus z1 mod of x2 minus z2 and so on. So this will be less than or equal to this upper bound. So hence we know that hence we have that d of xz less than or equal to d of xy plus d of yz, which is our required triangle inequality. Hence x d is a metric space.